This video is about finding the area of a surface of revolution. So this should remind you of the work we did back in chapter 6, where we would take a curve, we would take a region and revolve it around an axis and find the volume of that thing. It's the same idea, but we're finding the surface area of the thing instead of the volume of the thing. Now, it's sort of questionable whether or not AP really asks these questions on their exams. Whether or not they do, it's a pretty simple extension of what we've done so far, and so I think it's worth talking about. So in this first segment of this video, I just want to talk to you about where the formula comes from, because I feel like the whole point of all these things is for us to understand that the integral just adds stuff up, and if we choose carefully what to feed the integral to have it add up, we can have that thing mean something. So the idea is, imagine that you have some function like this, right? And they ask you to take, let's say between 0 and a, they ask you to take this section of the curve and sort of revolve this thing around the x-axis, right? When we revolve that thing around, I presume that all of us understand that we get a really wide and kind of ugly vase shape. I could have made it prettier if I'd sort of put the curve, down here a little bit lower, but that's okay. I'm not very good at making vases. That's okay. If I want to find the area of that surface, right, we would sort of need to think about, like, well, all right, if I had this thing sort of revolved around here, and if I were then to start cutting this thing into sections, right, if I looked at any one of these sections, and I don't know that I'm really going to try and draw the three-dimensional shape for that, but if I looked at any one of those sections, we're sort of going to have almost like a mini cylinder can type thing. And this time, so again, it's sort of like our disk method cuts, right? This is one of those disk method problems, right? But I'm not looking at the volume, I'm looking at the area. So if you had one of these disks or one of these cylinders, the surface area of that cylinder would effectively be 2 pi rh, right? And so what I'm going to be looking at doing here is I'm going to be looking at effectively, like at sort of a conceptual level, taking the integral of 2 pi rh. But we need to deconstruct so in this case, what is the radius of this can? What is the radius of the cylinder? What is the height of the cylinder? Like, what are these things? And the 2 pi is clearly a constant that's just going to sit out front. But in the context of this problem, what is the radius? Well, if I am revolving around the x-axis, then my radius will effectively be whatever the function is. The function written as a function of x. Okay? The confusing part is, what is the height? In the problems we used to do back in chapter 6, when we would revolve something around, we sort of took these small cuts. Our height of the thing would always be, like dx. The thickness of the thing would be dx. And in this case, that's sort of close to true, but the reality is, in this case, I'm not measuring volume. I actually want to measure distance. I want to be looking at that thing. But this should remind you of the video we saw earlier today. We were sort of talking about the arc length of these things. This h is effectively going to be the integral expression that we use for our arc length. Right? So when it boils down, like what it comes down to is that we can find our surface area by doing 2 pi times the integral of f of x, that represents the radius, times the square root of 1 plus f prime of x squared dx. And to me, this formula screams surface area of a cylinder. I see this as 2 pi r h. And if we can just remember that those are the pieces that we have, we're fine. I should mention these problems can also be done by revolving around the y-axis. When you revolve around the y-axis, you just need to pay attention to thinking about what your radius is, what your height is, and just sort of constructing those things in the right way. So we'll look at some examples here real quick, and hopefully they'll make lots of sense. So my first example, find the area of the surface formed when y equals x cubed on the interval from 0 to 2 is revolved about the x-axis. So I would definitely recommend you guys pause the video, make a little sketch of the thing, see if you can see where these things are, and sort of come up with the integral expression and then the area. I believe that this is one that we can take the integral of by hand, so don't just run straight to your calculator to find what the volume is. So the graph of this y equals x cubed between 0 and 2, effectively looks like that. I'm taking this and revolving it around the x-axis, so I end up with a surface that, sort of looks like a really, really wide Hershey's Kiss, I suppose, or maybe a tack. So this is this thing that I'm working with. when I revolve this thing around, my radius is going to be, the height of the function. So my radius is going to be x cubed. And remember that sort of the height of the thing will be our arc length, right? So I'm going to be looking at this as the surface area is 2 pi times the integral from 0 to 2. Then I put my radius expression here, that's x cubed. And then I have my arc length expression, which is 1 plus the derivative, that's 3x squared dx. Okay, and on the surface, surface area problem. On the surface, this may look like a crazy integral. Turns out it's really not bad at all, because this ends up being 9x to the 4th inside, which should be really simple for you to do. If you can't do that one, pause and think about it for a minute, because I assure you can. It's really, really straightforward. For this integral, we just need to do a u substitution. U is 1 plus 9x to the 4th. That means my du is 36x cubed dx. So then sort of as we're used to doing, we do dx equals du over 36x cubed. And then we're going to sort of substitute this all back into our integral expression. 2 pi times the integral of x cubed times the square root of u times du over 36x cubed. Very conveniently, the x cubes will divide out. I'll pull that 36th to the front. So the surface area will be 2 pi over 36, so pi over 18, times the integral of the square root of u du. Okay. Notice I'm not changing bounds. I could change bounds, but I will often just do this and then convert back to x and use my original bounds. So that's what I'm planning to do here. So my surface area should be pi over 18. So the integral of the square root of u, that's u to the 1/2. So we'll have u to the 3/2 times 2/3, which will reduce down to a 9. So that's the result of my integral. So I have pi over 27 times, and this is where I'm going to do my substitution again. I had 1 plus 9x to the 4th, all to the 3/2, and this entire thing is being evaluated from 0 to 2. So I said we could do this by hand. I didn't say we were going to get a marvelously pretty answer, but we're almost there. So the surface area, I've got pi over 27 times. Now when I evaluate for 2, I'm going to end up with 1 plus 9 times 16, which is 144 to the 3/2 power, minus pi over 27 times, plugging zeros a lot easier, we just get 1 to the 3/2 power. Now that I see this, I'm liking the idea of keeping the pi over 27 up front. Inside of this thing, I'm basically just going to have the cube root of 145 squared minus 1. And that's what the surface area of that thing we just figured out was. So again, not a marvelously pretty answer, but on the other hand, we got it. We found the surface area. I'll mention again, I don't know that these problems are commonly asked on the AP exam, but I do feel like it's a very simple extension of the calculus that we already know, and so it's worthwhile for us to see this and understand it. And I think the thing that's most important to me about all of this is that we see where the formula comes from. We see that this integral is effectively just adding up the idea of 2 pi RH. Like we're effectively adding up the area of sort of a slanted cylinder to find the surface area of this entire thing. So I do have one more example for us. It's related to the previous one, and I'm not going to have us evaluate it. I just want us to set it up. So I want to write an integral expression for the area of the surface formed when the same curve we did in the previous problem. So that curve was y equals x cubed. When that curve, oh, by the way, on the integral from 0 to 2, when that curve is revolved around the y-axis, right? So when I go around the y-axis, so what are we looking at here? We've got this curve again, from 0 to 2. I want to take that thing and revolve it this way, right? So pause the video for a minute and think about how you might set that up. I don't know that I want you to write anything down yet, but sort of think about how you might do that problem, and we'll go through it together. So one of the things that's important for us to recognize is that we're actually going to have to do this integral in terms of y. Right? And the reason we have to do it in terms of y is that in order for us to sort of use that slanted cylinder idea that we had previously, my cylinder is going to have to be oriented the other way. Right? I'm going to have to tilt the thing. So we'll sort of work through this here, right? How am I going to end up, like, effectively, what is my radius here, right? The radius of this thing is sort of this distance here, which we could call x, but I'm going to need to know what x is. I'm going to have to take this expression, and you'll remember we did this when we did all of our volumes, right? We would take this thing and rewrite it as x equals the cube root of y. It's sort of like this is the new function that we're working with, right? But, I mean, this interval isn't going to work anymore. That was an x interval. When I go from 0 to 2 on the x-axis, I go from 0 up to 8 on the y-axis, right? So the interval I'm working with is from 0 to 8, right? And so, you know, what do we have? We have our integral from 0 to 8. We have our radius, which was the cube root of y. And then we're supposed to have the square root of 1 plus the derivative of the curve that we're working with. And because this is in terms of y, inside here, we actually need like dx dy, right? We need the derivative of this curve that we're working with, right? Well, the derivative of that curve is 1/3 y to the negative 2/3, and that all gets squared. We put our 2 pi out front, and then we just run screaming from the room, because this is a mess. I mean, this is not a pretty integral, and that's why I only wanted us to write the integral expression for it. Right? So we had 2 pi, the integral from 0 to 8. We had the cube root of y times the square root of 1 plus, and I'm just trying to make my answer a little bit prettier, 1/3 y to the negative 2/3 squared dy. You know, we could throw this to the calculator. There's nothing wrong with that. But what I was looking at is just the idea of when we revolve these things around the y-axis, if we're going to use our same conceptual understanding, we need to change everything to be in terms of y. Our interval needs to be in terms of y. Our function needs to be in terms of y. The entire integral is in terms of y. Everything changes. So hope that made sense. Hope you know you guys are getting that and sort of seeing conceptually where it comes from. So I'll see you in class.